So this is a special topic, and it's specifically about building fragments when you are trying to interpret NMR. And all I need to say here is you need to think Nike. Just do it. There is no better way of doing this. This is the systematic way of approaching compound identification. If you are doing it any other way, you're doing it the hard way, and there's no reason to. Even if you are exceptionally good at NMR, this is the systematic way to approach it. This is the algorithmic way to approach things. You absolutely want to work this way if you can. And what do I mean about building fragments? Well, I mean, if I'm going to start diagramming out NMR for you in class, I always start drawing things like this. Why? Because it communicates a lot of information. I'm telling you that I have a methyl group, and I'm telling you that it's not near any particular functional group, and I'm telling you that there's one hydrogen neighbor, and I'm not specifying what's out here, and so on. This would be a fragment I would draw a lot. Or, I tend to do these a lot for methyls, as you'll see, and the reason why I do that is because often those are the easy peaks, and so I might very well do something like, say, this, where here I'd be saying, hey, listen, I don't know what's on the far side of that oxygen, but I'm looking at a shift that's near 4 because I'm near this oxygen, and there's 2 hydrogens in this environment, and it's a quartet, so that means I know that there must be 3 hydrogens out here, and so on and so forth. Again, it's incredibly powerful to use all 3 facets of an NMR peak, all 3 pieces of information for an NMR peak, and build a fragment. If I draw something on the board, you will be able to extract from it all 3 pieces of information more often than not, and therefore you can build an incredibly powerful fragment. Because if I look at this peak right here, it contains information about what's next to it in terms of functional groups. It contains information about how many hydrogens are in that environment, and it also contains information about what's next to it in the molecule. And if I combine all 3 pieces of information, what that gives me is not just the hydrogens I'm looking at, but the stuff that's around it. And if all you're doing is looking at multiplicity, then you're only looking at that. And if all you're doing is looking at integrals, you have no idea what's next to it. And if you're not paying attention to chemical shift, then you might miss where in the molecule you are. So you really need to pay attention to all 3 pieces, and you need to draw fragments. And the only reason why I drew a couple of fragments here that are unrelated to this molecule is because I want to illustrate some common themes. Always what I'm doing is I'm drawing out the hydrogen of interest. Always what I'm doing is drawing out whatever neighbors, whatever shape is associated. And always what I'm doing is not specifying the pieces that I cannot possibly know. And so there will be times where you don't know much about what's around, and there's a lot of unknown things. So for instance, if I have a methyl singlet that isn't anywhere in particular in terms of chemical shift, then I really can't specify what else is out here. It's entirely possible that I don't know at all, and I just know that I have a CH3. Sometimes it's all you know. But even if all I know is that I have an isolated CH3 with no neighbors, that ends up being fairly powerful. It tells me what can't be there. And even if all I know is that it's not next to any particular functional group, then again, that tells me it's kind of at the end of a chain. So there's a lot of power always in these fragments. So you want to get used to drawing this. You want to be able to draw the number of hydrogens in the group that you're looking at, which nearby neighbors it must have, and you need to interpret things about chemical shift as well. And take advantage of these squigglies. The squigglies tell you, hey, listen, I don't know what's there, but it's not hydrogen. That's usually the way I use a squiggly. I don't know what's out there. It could be anything, but not a hydrogen. So I specify hydrogens by drawing them out, and not hydrogens with the squigglies. Okay, so how do you build a fragment from scratch? Well, the thing I pay attention to first is the integration. How many hydrogens are in this environment? And unless you suspect symmetry, what that means is you're going to start by drawing a carbon, and then you're going to draw the number of hydrogens involved. And so here I've told you it's 2H, therefore I need to draw 2 H's. Simple as that. So there they are. Okay, then the next thing I do is I pay attention to the chemical shift, because that usually tells me what's nearby. So what else is out there? And so if I'm around 3 or 4, then I might draw an oxygen over here. If instead I'm around 2, then I might draw a carbonyl right here. If instead I'm like 1.7, that means something else, and so on and so forth. What is out there, what functional group you're next to, is often what I reach for next, because ordinarily what I'm doing is I'm trying to figure out integration, because that has to work, and then shift within a given range, so I suspect what's out there. I may not know, I may have a squiggle because I'm not sure, but I will almost always try to make a guess as to what'll be out there. And sometimes it's definitive. Right around 2, again, near a carbonyl or maybe near a benzene ring. Right around 4, probably near an oxygen, unless you suspect you have a chlorine, stuff like that. Okay, so right now we've used 2 of the 3 pieces of information, and then comes the last piece, which is how many neighbors does he have? And so right there, a triplet means that I must have 2 neighbors, and so I don't know what's out there, but it's not an H. Meanwhile, I have to have 2 hydrogens, because because of the multiplicity. Now, of course, you realize I just made an assumption. It is possible that this fragment shouldn't be like this, that instead what I should have is something instead more like this, and you can't necessarily rule this out at a glance, but it is something that you want to keep in mind. So I'm going to draw something new again. Now I've got the two hydrogens involved as before, but I can end up with a triplet because of one hydrogen each on either side. So even if I draw one of these fragments, sometimes I need to pay attention to the fact that this is possible, this is plausible, and again, my shift will have a tendency to guide me toward which of these is more likely than not, and so on and so forth. But even if you draw this and then later regret it, you can go back there. As long as you start drawing out these fragments, you're drawing the assumptions you've made. And so if you cannot make the system work after drawing a bunch of fragments and figuring out, okay, this really doesn't fit together and it doesn't make sense and so on, then you have the capacity to go back and change some assumptions. So what I would do, faced with the peak in the first case, is draw this first. And if it turns out that it doesn't work, no matter how hard I can make it work, then I might start thinking about this instead. So that's the way to approach compound identification. Build fragments. If you're doing anything else, you're doing it the hard way. I can't say you're doing it wrong exactly, but you're definitely doing it the hard way. Harder than is necessary. This is the easy way. Do it this way.